today we want to give you guys the zeta 2n values. Basic n is even. Oh, it's too large. So in our previous result, we already proved that zeta 2 is pi squared over 6, and zeta 4 is pi to the 4th over 90. And we want to prove, we also prove that zeta 6 is pi to the 6 over 945. So you can see my previous 3 videos about this. But in order to show the all the positive even value for zeta 2n, like zeta 8, then it's most common. It's convenient to use another variable, another coefficient called Bernoulli number. So let me read. So this is the definition of the Bernoulli number, that you just write it as x divided by e to x minus 1, and you write it as this. So you can compute like b0 is 1, b1 minus half, b2 is 0, and keep doing. I guess b2 is not 0. Okay, maybe. So I need to check, but you can just return the expression down. Okay, and next we can see the coefficient. Basically the coefficient is like you just write down, and notice that the odd index Bernoulli number is 0, except for b1. This can be seen by, if you write x equals to you divide by you multiple exponential minus x into this, and return into the odd function. So basically, except for b1, then all the other Bernoulli numbers are equal to 0. Okay. So once we have this definition of the Bernoulli number, then we can solve the zeta 2n values. To solve this, then let me show you guys step by step. Okay, so when we start, then we start from this formula. Okay, let me reduce my handwriting. Okay, so first we need to prove this identity. Okay, so the pi x times cosine tangent pi x equals to this. So to prove this, we just write this pi x cosine tangent pi x into cosine divided by sine. So cosine, this is the cosine, this is the sine. So remember, cosine x equals to exponential ix plus exponential minus ix and divided by 2. And the sine is similar, but just divide. So plus sine become minus sine divided by 2i. So basically, this first term is correct, and we multiply them by exponential I pi x, so it becomes this. Or you can see my cursor, and then we can write it as this, right? Because we just extract 1 exponential 2 pi x, and we times I pi x into this, so we become this. And the first one is we just preserve it, and the second one is the standard Bernoulli number. We just write it down, it becomes this. And then we change this to be 1, right? Because you can check that b0 is 1 and b1 is minus a half. So for n equals to 1, the I pi x term cancelled, right? This is because this x cosine cotangent pi x is an odd function. It's an even function. So the odd term x cancel, right? So you get this. And finally, you just write this. You just write half and multiple half, multiple twice and divided by half. Then you got this. So you can see this 2n factorial b2n 2i pi x 2n. So we can compare this to this. Then we get our coefficient. we get our coefficient. So the remaining thing is we want to check how this pi x cotangent pi x is equal to this one. So we prove our lemma, right? So this is the lemma. So proof this we use the standard Taylor the sine function expansion. So you can check that this is easy because when x equals to integer, then the right hand side will be 0 because sine will be 0. Sine plus minus pi is 0, sine plus minus 2 pi is 0. And you take the log on both sides. So the log a divided by b will be log a minus log b. So you have this one, and the product becomes a summation. So this is this one. And you differentiate both respect to x, so it becomes sine pi over x. The differentiation of sine is cosine, so the chain rule will be another pi, so pi becomes this. And then this is 1 over x, and then you just do this. And then when you do this, you do it carefully. The left hand side becomes the standard pi x cosine pi x, and the right hand side is 1 divided. Oh, by the way, because you times x, so both you need to times x both, so you get x squared. So at this moment you have this. Okay, so let me use to eliminate some. And finally, you use the geometry series. Right? Basically, you use this. Basically, you use this. You use this on this term, so you get this. Right? So basically, you get 1 minus x squared divided by k squared become x k squared. Right? Use n equals 0 to infinity, so become this. And this term just minus 2 just go out, and then this x squared times in it, right? Because and we change n from 0 to 1 due to this 2 factor multiple x this x squared term. So we have this, and we x squared 2n term, and we exchange the sum of n equals 1 to infinity k. We got this, and n preserved, and this is a zeta to n. Right? Remember that zeta to n just divide just take to the 2n k from 1 to 0. So basically we have this. Okay, so basically we have this lemma. Then we already know from this lemma we can expand the left hand side into the Bernoulli variable, so that we can relate the zeta the zeta positive even integer values to the Bernoulli numbers. Okay, so basically this is a whole video for it. This is because this proof is somewhat complicated, so I just used some Wikipedia result but explain the steps. Okay, I hope you guys love this video. If you want to see more interesting mathematic video, then subscribe to my channel. Thanks.